Hello guys, let's talk about the first digits of powers of 2. Just take number 2 and raise it to different powers. Well, for instance, first 16 powers of 2. 2, 4, 8, 16, 32, 64 and so on. And pay attention to the first digits in decimal system, of course, of these powers. 2, 4, 8, 1, 3, 6, 1, 2, 5, 1, 2, 4, 8, 1, 3, 6. At first sight, well, nothing interesting. However, let's calculate the frequency of each of the digits. And among these 16 powers of 2, the first 16 powers of 2, we'll have such frequencies. Well, we see that 1 is the most frequent digit, and 7 and 9 are the least frequent. Actually, they didn't even appear. Well, the question is, what if we take not 16, but much more powers of 2? What if we try to calculate these frequencies up to infinity? Well, this is the table of the frequencies among first 16 powers, and we need a definition of a frequency among all natural powers of 2, among all positive integer powers of 2. And the most natural definition of such frequency is, of course, the limit when we take some n, which tends to infinity, and among first n powers of 2, how many times did we have the first digit 1 and the first digit 2 and so on? So we just calculate the number of times for each digit and divide this by n, the amount of powers of 2, and see whether it tends to some certain number when n tends to infinity. And we will see that these limits exist for every digit, and these are the values we will obtain. So now I will show how to calculate the frequencies. First, transform the condition that k is the first digit of 2 to the power of m, transform it into a more convenient form. Well, on the first line, you see inequalities that 2 to the power of m is greater than k multiplied by some power of 10, which simply represents a number of the form k00000, and 2 to the power of m should be less than k plus 1 multiplied by the same power of 10, which means that 2 to the power of m is less than k plus 1, a digit 00000 and so on. Then apply logarithm base 10 to these inequalities and obtain that logarithm k plus l and logarithm k plus 1 plus l are the two bounds of m logarithm 2. We need to get rid of l, because it doesn't matter what l is equal to. All that matters is k. So we go to the fractional part of all three values and finally end up with the fact that m multiplied by logarithm 2 base 10 should be inside an interval or a semi-interval between logarithm k and logarithm k plus 1. And this looks very familiar. So remember, or just notice, that logarithm 2 is an irrational number. Please spend some time to prove this. I will leave it to you as an exercise. And from this fact, and using Weyls' theorem, we can calculate the precise limit of times of frequency when m logarithm 2 is indeed inside this interval. So from logarithm k to logarithm k plus 1 is the very interval I which we used to denote the interval in Weyls' theorem. And we know that the frequency is actually equal to the length of this interval. So the answer is very simple. The frequency of k as the first digit of power of 2 is equal to logarithm k plus 1 minus logarithm k, all base 10. For instance, if we go back to the table of frequencies, let's say, how do we calculate the frequency of 5? How often does 5 become the first digit of power of 2? Well, we simply subtract logarithm 5 from logarithm 6, and it is approximately 0.079. Of course, all of these values are approximate. None of them is actually a rational number. And using the same formula, you can calculate all the other frequencies.